Okay, so we will start with some basic work in kinematics. Okay, so I'll just start by explaining this question. So what is happening is that at time t equal to 0, a ball is dropped from the top of a cliff like this. Okay, and then there is like this slot in the cliff, or like a cave in the cliff, which is of height h at a depth of h1 from the point where it has been dropped. Okay, so the height of this cave is given to us to be 10.2 meters. Okay, and the person who is standing inside the cave observes the ball going past the cave. So if the balls reach the top of the cave at some time t, then it crossed the bottom of the cave at time t plus delta t. So this delta t time is given to us as 0.2 seconds, and g is the standard value. Okay, like this. And further, the floor below the cave, that is at a further depth of 44.8 meters given to us. Okay, so what we have to calculate over here is this value h1, that is what height the ball was dropped from. So we have to find h1. Okay, then if the ball appeared here with a speed of v1, then we have to find the value of v1 also, and we have to also find after how much time from t equal to t plus delta t onwards, that is after the ball has crossed this floor point, after how much further time the ball hits the floor. Okay. So in terms of concepts, this is a very easy question. As you know, it's just based on free fall, but I just want to discuss certain tricks and concepts that we can use to solve something like this fast and accurately. Hope the question is clear to all of you. You can turn your mic on and ask me if there is any doubt or any question you want to discuss. Yes, Somadeep, I have seen the doubt. I will be taking up the doubts at some point of time. Or if I'm not able to take up all the doubts today, I will be sending you some solution or hint for it. Because with less number of sessions left, with respect to your JEE Advanced exams, you want to cover all the concepts at a problem solving level at the JEE Advanced level at least once from the entire syllabus, each and every chapter, every concept. If you got the answer for H1, please. Yes, Aditya, that is correct. Very good. Yes, that's correct. Very good. Okay, so I'm just putting the answer so that you can verify. So this h1 you should be getting as 125 meters. This v1, the velocity just at the top of the cave in the cliff, this we should be getting as 50 meters per second. And after how much time from this, okay, so this time interval come out to be 0.8 seconds. Okay, now I'm going to tell you a trick method that I tend to use for these type of questions. And that trick method is that whenever we have uniformly accelerated motion, okay, if the acceleration vector is constant, okay, then v is equal to u plus at. This also means that average velocity in a certain interval is u plus v by 2. And this is something very useful. And the displacement in a certain interval becomes the average velocity multiplied by the time interval. So I'm going to make use of this over here. Okay. So when the ball started from here, u was 0 and it has an acceleration of g equal to 10 meters per second square. Okay. So if it reaches here at some time t, then this velocity v1 is equal to gt. Okay. And then it reaches here with a velocity v2, let's say, at t equal to t plus delta t. Okay. And this distance from here to here is h. So we can see that in this interval for h, the average velocity is v1 plus v2 by 2. Okay. And that v1 plus v2 by 2 into this time interval should be equal to h. So we have our first relation that v1 plus v2 by 2 into 0.2 seconds, because given was that h is equal to, how much was it, 10.2 meters, and delta t was equal to 0.2 seconds. So this is equal to 10.2 meters. So this is the first information. Okay. And the second thing that we have is that v2 is equal to v1 plus g delta t. So v2 minus v1 is g delta t. So v2 minus v1 is equal to 10 into 0.2. So v2 minus v1 is 2 meters per second. This is our second equation. Okay. So from this we are getting v1 plus v2 . This was the data, right? Yeah. Is 10.2 into, I mean, divided by 0.1. So that's 102 meters per second. And from this we are getting this. So we just subtract the two equations. Okay. We get 2v1 is equal to 100 meters per second, which means v1 is 50 meters per second. which means that t is equal to 5 seconds. Okay, and t plus delta t is equal to 5.2 seconds. So if you get used to this method of using average velocity, it can sometimes be very convenient to solve. Otherwise, you can use the standard equations also. There's no problem with that. But this can be a very convenient way of solving problems, especially when g is given to you as 10. So it's very easy to calculate. Okay. Now you can also see from t equal to 0 to t equal to t, which now we know is 5 seconds. U is 0, v1 is 50 meters per second. So average velocity in this interval of time is 50 by 2 or 25 meters per second. So this height h1 that we have to calculate, this one h1. So h1 should be equal to 25 meters per second into 5 seconds. So it should be 125 meters per second. Okay. And now the third thing that was given to us is that from here further down, this height was, if I'm not mistaken, 4.8 is sorry 44.8 meters. Okay. So h2 was 44.8 meters. Okay. So now you can see that t equal to 0 to t equal to capital T, the total displacement is h1 plus h plus h2. So that is 125 plus 10.2 plus 44.8. So that is 125 plus 55, right? So that is 180 meters. So half gt square is equal to 180 meters. So from this you get the total time as 6 seconds. So total time is 6 seconds means that further interval of time t minus t plus delta t, that will come out to be 0.8 seconds. So I'm just providing you with an alternate method of solving these type of problems, which sometimes is very useful. Okay. All right. Now next up, so don't worry about the solution. I'll provide you with the notes and everything. So, okay. Next up, we are going to do some questions based on relative motion. So now we have this kind of a situation. We have a smooth inclined plane which is at an angle alpha, and on this smooth inclined plane we have a thin plank. It's the thin plank of length L. Okay. And on the plank we have a particle P. Okay. Now this particle is projected at some speed u at an angle beta with respect to the plank. Okay. So the particle P is projected from the plank's corner initially the plank being at rest at t equal to 0, and simultaneously the plank is released. So we have to find the minimum length L of the plank such that the particle returns to the plank. Hits its surface again. So we want to find this minimum length in terms of the quantities given U, alpha, beta, and G. So you have to give the answer parametrically in terms of these quantities which are given. So in a sense, you can say this question combines a bit of Newton's laws with projectile motion also, because the plank is sliding down the inclined plane. That is a projectile. That is a Newton's laws problem. But basically, what I want to focus on here is that how you can make use of relative motion to make this problem solving easier. So initially, both the plank and particle are at rest, and then we project this particle like this, and at the same instant when this is projected at t equal to 0, the plank is also released. So the plank starts sliding down the incline. Yes, Samadip, that is correct. Very good. Yes, Nishit, that is correct. Good. So basically, the situation that we want is that at t equal to 0, if this is how the system looked, then after some time, when the projectile has completed its path or whatever, okay, suppose the plank has come here by then. So if this is just about reaching, the limiting condition is just about reaching this. So then this is where they should land at t equal to capital T. Okay. So that's one way of solving it if you're looking in the ground frame. Okay. So remember, this will be accelerating at g sine alpha like this. Okay. Whereas the particle during its motion will be having an acceleration of g vertically downwards. Okay. But the easy way to solve this would be that if you are in the Planck's frame, okay, so first of all, you take this as your x-axis and take this as your y-axis. Okay. So as the Planck is moving, okay, and as the projectile is moving, okay, the acceleration of the Planck is g sine alpha I cap, whereas the acceleration of the projectile is g sine alpha I cap minus g cos alpha j cap. So from this you can see that the acceleration of the particle, okay, this is for the particle, acceleration of the particle with respect to the Planck is acceleration of the particle in the ground frame minus acceleration of the Planck in the ground frame. So that is just minus g cos alpha j cap. So this makes life very easy. Okay. And the initial velocity of the particle was that u, okay, u cos beta I cap plus u sin beta j cap. Okay. Whereas the, sorry, let's not box this. Whereas the initial velocity of the Planck started from rest. So that's 0. Yes, that's correct, Ashish. Okay. Just a minute, I'll share the file again. Okay. So the initial velocity of the Planck is 0. So this tells us that the relative initial velocity of the Planck, or rather the particle with respect to the Planck, is very easy. It is u cos beta I cap plus u sin beta j cap. So now this we can relate with the regular projectile motion. So what we can say is that for an observer who's standing on the Planck, so in the frame of the Planck, the particle here, it has started with an initial velocity which is like this. This is the initial velocity of the Planck particle with respect to the Planck at an angle beta. But as the particle goes in its path, it has an acceleration which is in this direction. This is the acceleration of the particle with respect to the Planck. So in the Planck's frame, the range of the particle with respect to the Planck will become u square sine 2 beta divided by this acceleration of the particle with respect to the Planck. And that is equal to how much in magnitude? That is equal to g cos alpha. Okay. So this range is equal to u square sine 2 beta divided by g cos alpha. And this range should be less than equal to L. So that's why the minimum value of L, as quite a few of you have correctly got, should be this. So this is one of the advantages of using relative motion. Whenever we are comparing the one motion of one moving object with respect to another moving object, there is always a benefit in using relative motion as opposed to individually solving their motions. We can also solve this by individually solving the motion of the Planck and the particle. Okay. So some of you might have used that also, but it is advantages here. It's like a one-line solution. Like I've taken time to explain all these things, but the moment you realize that in this frame is like a, it's like a virtual gravity or like an apparent gravity that's acting normal to this surface. So it's basically like a regular parabola with x and y axis like I've drawn as the symmetry axis. But just replace g with g cos alpha. Okay, next let's move on to another question. Now we have an object that is moving at a constant velocity v naught like this on a horizontal path, straight line horizontal path. And this is the position of the object at t equal to 0. Whereas from this position B, okay, so the xy plane is the horizontal plane. So the acceleration due to gravity is minus 10 k cap meters per second square. Now A moves at uniform velocity of v naught I cap as shown. And this distance is 1600 meters. Now at t equal to 0, okay, a projectile is fired from B to hit A. Okay. At some time, capital T. So first of all, find the minimum projection speed needed and the direction cosines, that is cos alpha, cos beta, and cos gamma for the projection velocity with respect to xyz axis, okay, for u being minimum. So this combines a bit of vector algebra along with projectile motion concepts. Sorry, this is 160 meters, okay, not 1600 meters. Just take the value d as 160 meters. This angle is 90 degrees. Yes, Ramadip, very good, that's correct. Yes, that's correct, Samadhi. But I think your alpha, beta, gamma is interchanged. Just check once. Okay, so let's understand this. Now, let's say that at some time t, this one reaches here, and the particle that was thrown from B, it actually goes in a projectile path like this. So the projection of that on the horizontal plane is this. This is the displacement of the projectile, but the actual path is like this. Okay. Yes, Nishit, very good. That's correct. So you can see that suppose if the projection velocity at B is ux I cap plus uy j cap plus uz k cap. Okay. Then the displacement of B as a function of time. Now, obviously, acceleration of the projectile is minus g k cap. Okay. So the displacement of the projectile as a function of time is going to be ux t I cap plus uy t j cap plus uz t minus half gt square k cap. Okay. So at t equal to capital T, ux into t should be equal to displacement of E along the x-axis. So that should be equal to V naught E. So that tells us that ux has a fixed value of V naught. Okay. Uy into t should be equal to distance d. Okay. And uz into t minus half gt square should be 0. So t is equal to 2 times uz divided by g. So from that you can see that uy into 2uz divided by g should be equal to d. Okay. Now our u is equal to square root of ux square plus uy square plus uz square. Okay. So that is equal to square root of v naught square plus uy square plus uz square. So you can see that u will be minimum if uy square plus uz square is minimum. So in this, what we can do is we can take uy as x. So from here, uz is equal to d divided by, sorry, d into g divided by 2 times x. So x square plus dg upon 2x whole square is equal to uy square plus uz square. So this has to be minimized. Okay. So the quantity x square plus d square g square upon 4 x square. Let's say this is the function. This has to be minimized. Okay. Or there's another way you can understand this, that let us take uy square plus uz square as some u prime square. Okay. And uy becomes u prime cos theta, and uz becomes u prime sine theta. Okay. So now we can see that from this relation earlier that we have got for this thing, that d is equal to uy into 2uz by g. We can see it is equal to u prime square sine 2 theta by g. Okay. So you can see that u prime square is equal to dg upon sine 2 theta. Okay. So this is minimum when this is maximum. Okay. So u prime square is minimum is equal to dy. So dg. Okay. So our d was 160 into this. So 40 meters per second. Okay. So u's minima, u prime's minima, will become square root of v naught square plus uy square plus uz square's minima. So that is v naught square plus u prime square's minima. So that is 50. So that's one way you can do this, or you can use the AMGM method for this. You can use this method, that x to the power 4 upon plus c upon x square. This is the function of x. So this is minimum when x square is equal to c. So you can use AMGM method to find minimum also. Okay. Anyhow, but all this apart, I'm just going to show you the easier method, that is the projectile motion, the relative motion method. Okay. Once you realize that E's velocity being v naught I cap, and the projectile's velocity as a function of time being v naught I cap plus some uy j cap plus uz minus gt k cap. If you look at the velocity of the projectile with respect to A, you can see it is uy j cap plus uz minus gt k cap. So relative to A, okay, the motion of the projectile is a parabolic path in the YZ plane. This kind of motion. Okay. Y component of displacement is uyt. Z component of displacement is uzt minus half gt square. Okay. So the initial velocity of the projectile with respect to A, that is uy j cap plus uz k cap. Let us say that is some u prime cos theta j cap plus u prime sin theta. Okay. So therefore range of P with respect to A, that should be D along the y-axis. Because to A, it will look like the projectile just came like this and hit it here. So the range is along the y-axis. Okay. So from this and this, you can see that D should be equal to u prime square sine 2 theta by g. So u prime square's minima should be equal to g into d for theta equal to 45 degrees. So because these are mutually perpendicular, so you can see that the initial velocity of the projectile okay. So this is minimum when uy square plus uz square, that is minimum. So that is this condition. So having understood that now, so we can see that this u prime we just saw is square root of 10 into 160 or 40 meters per second, and this theta was 45. So uy is equal to uz is equal to 20 root 2. So u, initial velocity of the projectile, is becoming v naught I cap, which was 30 I cap, plus 20 root 2 j cap, plus 20 root 2 j cap. So hence now you can see the direction cosines is remember cos alpha is x upon this thing for a vector like that. So using this, okay people, so hope this question is clear to all of you. So to visualize in the relative motion is the easiest way. If you're sitting on that object A, which is moving at the constant velocity v naught I cap, the projectile should look like it's started at a point away from you on the y-axis. So it's moving in the xy plane and coming and hitting you. So its projectile motion relative to A is only happening in the yz plane. So it's very easy to calculate that trajectory and the condition for minimum projection velocity with respect to A. And then in the ground frame, we just have to add a component which is perpendicular to that plane. So the condition for minima remains the same. The condition for the minima of U in the ground frame is the same as the condition for minima of U prime in the relative frame. Only the values are different. U prime's minima is 40, whereas in the ground frame, U's minima is 50, because there is that added component of 30 I cap. That is the whole point that I want to discuss in this question. Okay, now we will move on to another type of question, which again includes a bit of dynamics in our understanding of uh, kinematical problems. So next example, what we have is a particle is projected horizontally with some velocity v naught in a vertical xy plane. So a particle of mass m is projected like this. So it goes into this kind of path. But along with gravity, okay, there is also a viscous force or a viscosity force, or you can say a drag force, given by the relation F is equal to minus alpha V acting on the particle. Okay. So at any instant of time, if the particle is here, there is, or rather there are two forces acting on it. Viscous force and gravitational force. Alpha V in magnitude, but in direction, you can see it is opposite to the velocity. Like this. Okay. So if the speed of the particle after a very long time becomes constant or terminal speed, okay, at V terminal equal to 2 V naught, then first of all find alpha in terms of V naught M and G. Okay. And secondly, find the particle's acceleration at t equal to 0. Third, find its velocity v at an instant when the horizontal component of velocity has become v naught by 3. Okay, so let's check out the value, people. Yeah, Nishit, Ashish, and Somadeep, the value of alpha is correct. So in this question also, if we take a vector approach, we can simplify things. Okay, so we can say that at some instant of time, when the particle has reached here, this velocity is some Vx I cap plus Vy j cap. In fact, we'll benefit if we take the y-axis downwards. The y-axis downwards like this. Now the force acting on it at that point of time is like this. So the net force, which is the mass into acceleration, is mg j cap minus alpha into Vx I cap plus Vy j cap. So you can see that the acceleration's x component is minus alpha Vx. So dVx by dt is minus alpha Vx. So this is a very standard operation, that exponential function that we get. So V naught to some time t to some value Vx times 0 to t. So solving this, you know what to do. You'll get the standard value that Vx is equal to V naught e raised power minus alpha t. ऐसा आ जाएगा. Or alpha by m. Minus. It should be alpha by m. Whereas the y component of acceleration, now that is the more interesting thing. That is g minus alpha by m. Right. So dvy by dt is g minus alpha by m vy. So from your experience in solving differential equations, various things, RC circuits, terminal velocity and viscosity and all this kind of thing should be very familiar to you. So this is this. Now Vy is starting from 0, because remember at t equal to 0, our initial velocity was V naught I cap. So our ux was v naught, but our uy was z. So this is going from 0 to t. So this will give us this kind of relation, that vy is equal to mg upon alpha 1 minus e raised power minus alpha by m. So this kind of a relationship between vx and vy. So this is our velocity as a function of time. Velocity as a function of time is v naught e raised power minus t by tau, let's say, I cap, plus mg by alpha 1 minus e raised power minus t by tau j cap. Okay, so let's come back to this. So here you can see that with this relationship, your terminal velocity is becoming mg by alpha j cap, and that happens after a very long time. So from this expression here, you can see that terminal velocity at t tending to a very large amount of time will become mg by alpha j cap downwards, that is. So that mg by alpha is equal to 2 v naught, because that is what was given to us. Okay. So first of all, that is our alpha. Alpha is equal to mg upon 2 v naught. Okay. So that's the first part's answer. Then the second thing, at t equal to 0, you can see that the initial velocity was minus v naught I cap. So the net force acting on the particle was, sorry, plus v naught. So minus alpha v naught I cap plus mg j cap. So the net force acting on the particle was the vector sum of alpha v naught, which will be how much? It will be mg by 2, because alpha is like this, and mg. So the acceleration of the particle will be like this. This will be the acceleration at t equal to 0. So the acceleration will be minus g by 2 I cap plus g j cap. But plus g j cap because I have taken my y-axis downwards. Okay. So this is the answer to the second part of the question. So I think this all of you have, most of you have got these two parts. Now we have to come to the last part, which is we have to find the velocity when the horizontal component of velocity becomes v naught by 3. Right, this part we have to discuss. This I'm not seeing the correct answer yet from anybody, so just try to work it out. Once I've written the velocity as a function of time, it should be pretty easy, which I have done above. Okay, so just follow that expression and you will get the answer. So, this type of question should not worry you. It is basically like, you treat it like a superposition of a motion along the x-axis with the initial velocity and only a drag force, and then a motion along a y-axis where the object is dropped. So there is mg acting on it downwards and a drag force acting in the opposite direction, and then superimpose the two. Now, individually, each is something you are quite familiar with. So the combination is not supposed to be very difficult. Shreya, this is the answer you're giving for alpha, or alpha's value is mg by 2 v naught. Okay. Yeah, Nishit, your answer is correct now. Okay. So see how I got the value of alpha, Shreya? No. Using these two expressions, I got the velocity vector as a function of time now. So at t tending to infinity, you can see that, or after a very long time, this exponential factor, this tends to 0. So Vx will tend to 0, whereas Vy will tend to become V naught. Sorry, will tend to become mg by alpha. And that mg by alpha is supposed to be the terminal velocity, which is given to us to be 2 V naught. So that's how we got alpha. Yes, Aditya, that's correct. Nishit, your answer is also correct. Very good. Okay, so third part, when Vx has become V naught by 3, that means V naught e raised power minus t by tau, where that tau is basically m by alpha. So this term is equal to V naught by 3. So that means that that exponential factor is 1 by 3, or this time is basically tau ln 3. Okay. So at that time, Vy will become mg by alpha into 1 minus e raised power minus t by tau. So just substitute this value here, that e raised power t by tau is this much. So that becomes mg by alpha, which is the terminal velocity. Okay. So 2/3 of the terminal velocity. Okay, and the terminal velocity itself was 2 v naught. So it is 2 v naught into 2 by 3. So 4 by 3 v naught is the y component. So the velocity is v naught by 3 I cap plus 4 v naught by 3 j cap. So the magnitude of that velocity is v naught by 3 into square root of 70. Yes. So finally, we can back calculate and get it in terms of v naught. Okay, now next thing we're going to discuss about the applications of the concept of relative velocity of approach or separation, whatever be the case. So in the case of two particles, if they have individual velocities which are, let's say, like this, which are at angles like this, then at any given instant, the instantaneous approach velocity is the rate at which the distance between them is decreasing. So the approach velocity of A towards B or vice versa is minus dx by dt. So that quantity, as you can see here, becomes VA cos alpha plus VB cos beta. Okay. So this concept of approach velocity is something that is very useful in a number of things, not just kinematics problems, but also in constraint relations, as we'll see later. Okay. So for example, we have something quite simple like this. Now at some point of time, let's say these two objects A and B are in motion such that these all things are given to us. So at an instant when VA is equal to so find the accelerations of A and acceleration and velocity of A and of B at the same instant. Yes, that's correct, Ganesh. Yes, Nishi, that's correct. Very good. So since we are just talking about approach velocity, I will solve this first part by using constraint relation using approach velocity. So if this part of the thread length is z, okay, and this part of the thread length is y. Now you can see that this point where the thread is connected, this is moving with an instantaneous velocity va. Okay, so if this point where the thread is joined is o, then the instantaneous approach velocity of that point A towards O is VA cos theta, and that is minus dz by dt. Whereas you can see that VB is plus of dy by dt. And you can see that z plus y is the total length of the thread, which is constant. So you can use this thing that minus dz by dt should be equal to dy by dt, or VA cos theta should be equal to V. So 1.2 centimeters per second into cos of 37, which is zero point 0.8, should be VB. So instantaneous VB will be 0.96 centimeters per second downwards. Okay. Now we will discuss the virtual power method also of doing questions like this, which might be more convenient in most of the cases, but you should know how to do this by this kind of method also. D is in centimeter. Okay, my mistake. It's in centimeters. Okay. Now the constraint relation for acceleration is a little bit more complicated, because you will understand one thing here. In this equation, all three quantities VA, VB, and theta, they are all instantaneous. Yeah, Ganesh, I will just verify the answer. So now this makes things a little bit more complicated. Now, when we have to rate of change this quantity, now there is no trick that we can use here. We have to basically find the relationship by differentiating both the sides of this equation for the accelerations. Sorry, this should be VA. So this will become rate of change of VA into cos theta plus VA into rate of change of cos theta is equal to rate of change of VB. Now this we can see is nothing but acceleration of VA, but this term will become minus sine theta d theta by dt. That should be equal to acceleration of V. So this we have to now figure out. Okay, so now coming back to the geometry of the problem, this distance was d, this angle was theta. So if this distance is x, we can see that x is equal to d cot theta, right? So dx by dt is equal to minus d cosec square theta d theta by dt. Now dx by dt we can see was minus va, because va is basically minus dx by dt. Okay, so minus va is equal to minus d cosec square theta d theta by dt. So we can see that theta is increasing because d theta by dt is a positive quantity, which makes sense because as this is moving here, theta would have increased, whereas x is decreased. Okay. So anyway, so d theta by dt is va upon d sine square theta. Is this correct? This is the same constraint relation you have got, Ganesh? Okay, very good. So that's what we substitute here. So acceleration of A cos theta माइनस ये कितना हो जाएगा VA by D, sorry, VA square sin cube theta by D will become acceleration of B. So this is what we'll have to substitute now. So at the given instant, acceleration of A was given to us 0.2 centimeters per second square. VA was given to us 1.2 centimeters per second, but D was given to us as, how much was it? 12 centimeters, was it? Yeah, 12, 1.2, 37.2. Theta is 37 degrees. So this will become 0.2 into zero point 0.8 minus 1.2 square upon 12 into 0.6 cube. That is acceleration of P. Yes, good. Okay, so this approach and separation velocity business can be used in a number of places. So I'll just give you very briefly two other simple examples. So I'm sure most of you are very familiar with these things, but I just want to go systematically and do a revision of all essential concepts for our upcoming JEE Advanced. Okay. So suppose we have something like this, rigid body dynamics. Now we'll see the full solving of this type of question and the rotational aspect of it also soon. But right now, let's say we are just concentrating on this, that we have a rod whose endpoints are sliding like this. When this angle is theta. So given VA is something, let's say 0.5 centimeters per second, and theta is, let's say 53 degrees, find the value of VB. So again, what we can do here is that the distance between A and B is constant. L is fixed length because it's a rod, it's a rigid rod. So approach velocity of A towards B should be 0. So VA, now this angle will become, let's say, phi. So that is 90 minus theta. So VA cos phi will have to be equal to VB cos theta. So this will become the relation. So VA sin theta will be equal to VB cos theta. So VB will be equal to VA tan theta. And then you substitute these values. Simple. Okay. Yes, that's correct. Bhumik and Aditya. Okay. So I'm sure you are aware of multiple ways of solving this type of question. But I'm just telling you how the approach velocity concept becomes important like this. Okay. Similarly, we have, let's say, another dynamical situation like this. Something like this is happening. Now we have a rod which is hinged at this point. Okay. And it's in contact with a block. Like this. Rod of length L. Now suppose we are pushing this block such that it has a velocity v naught like this. So we want to find the, so v naught is given, L is given, and theta is given. We have to find the angular velocity of the rod. Okay. So again, this is a classic situation where we can find the constraint relation by the concept of approach velocity. Okay. So the end of the rod here is in contact with the block. Okay. So let's say the point in the block which is in contact is B, whereas the point on the rod which is in contact is A. So what should happen here is that the point of contact of the rod A, actually not so much about the point B, but it's more about the surface. Okay. Point of contact of the rod A should slide tangentially on the surface. So the approach velocity of the point A with respect to the surface should be 0. So whenever we have a surface like this and a point is moving like this, the approach velocity is v cos theta, because it's the rate at which the perpendicular distance is decreasing. So here what is happening is that this point A, if this rod is rotating at omega like this, then this point has a velocity in this direction of L omega. Okay. And this surface itself is having a velocity of v naught. Okay. So this angle will be theta. So you can see that this condition will become that VA sine theta should be equal to V naught, or L omega sine theta should be equal to, so omega should become V naught upon L sine theta. So now in this we are incorporating the concept of approach or separation velocity of a particle with respect to a surface. So the relative motion of the particle with respect to the surface should only be tangential, should only be in this case in the vertical direction. Right? So that is the concept we are using. Hope this example is clear. People just go through it once. Okay. Now next, more standard type of applications of approach velocity in directly in kinematics type questions. So I'm just reminding you of this type of question. In the situation of particles chasing each other. So initially you have three particles on a two-dimensional plane lying at the corners of an equilateral triangle. Now A, B, and C start from position shown, continuously moving such that A's velocity points at B, B's velocity points at C, and C's velocity points at A, and the magnitudes of their velocities are all the same. Okay. So you have to find the time after which they collide. Yes, that's kind of standard problem. So I'm sure most of you are familiar with this. I'll just go through this very quickly once. So what is happening at t equal to 0? The velocity vectors will look like this. This is the situation at t equal to 0. But a very small time later, these particles have come here. Okay, so at t equal to delta t, now they form a triangle like this. Triangle of slightly smaller dimension, but still an equilateral triangle. And still, okay. So now their velocities will also turn like this because they are pointed at each other. So like this, they will go from triangle to triangle and they will take a curved kind of path each like this. And eventually they will intersect at the centroid somewhere here. So at any other instant of time also you can see that their mutual orientation is always going to be an equilateral triangle. So always the situation about their velocities is going to be like this. Okay. So even though the individual motion in ground frame is very complex, but always the approach velocity of A towards B or approach velocity of B towards C or C towards A is going to be constant, and that's going to be equal to V naught plus V naught cos 60. So that is 3 by 2 V naught. Okay. So if the instantaneous distance between them is x, so this minus dx by dt is equal to 3 by 2 V naught. So the triangle formed by them is of dimension x by x by x at some time t. So that dimension is decreasing at this uniform rate like this. Okay. So minus L divided by, I mean, this dimension changes by total amount of, this should be equal to 3 by 2, where t is the time at which x becomes 0, whereas x was equal to L at t equal to 0. Okay. So this is like one standard type of application of approach velocity concept when you have multiple particles chasing each other at constant speed. So it could be 3 particles at the corners of a triangle or 6 particles at the corners of a regular hexagon, or 4 particles at the corners of a regular square and things like that. So you have to use this kind of approach. Now at the end of today's lecture, I'll give you another problem of kinematics to use approach velocity concept. It's a bit of a lengthy problem, so I'm going to give it as an assignment for you and you can work it out and tell me. Now currently I'm moving on to more questions to do with involvement of forces, but where we have to use a bit of relative motion concept. Okay. So next example like this. So this surface has a coefficient of friction of 0.1. This surface has a coefficient of friction of 0.5. Okay. The mass of block A is equal to, let's say, 4 kgs, and the mass of the plank B is actually less and it is equal to 1 kg, and the length of the plank is 20 meters. Okay. Now A is given a sharp impulse initially. So the system is at rest and A is given a sharp impulse. so that at t equal to 0, A develops a velocity of v naught. So the system was at rest initially, and A is given a sharp impulse j such that its velocity v naught is, let's say, 8 meters per second. So given that g is 10 meters per second square and the length of the plank is 2 meters, find the time after which A slides off the plank. So assume A is a block of negligible size compared to L. Okay. So after how much time A slides off the plank? So just try this out, people. But Ganesh, have you checked for the condition that it may not slide off? Is it possible that it's not sliding off that condition? Yeah, that's the thing. We have to be careful in this question. Exactly. I think that's what's going to happen. It's not going to slide off. Okay, so let's understand the friction immediately when this starts moving at velocity v naught. Exactly, Nishi. Good. Okay. So then if that's not happening, then we have to find the maximum displacement of A with respect to, okay. So if not, okay, then find maximum displacement of A with respect to the Planck B. Okay. And then again, the maximum displacement of A with respect to ground. So let's understand this question in detail. Okay. Okay, Nishi. Yeah, that seems correct. Okay. So first of all, let's understand at t equal to 0, when the motion just about starts, how friction acts. Okay. So this block is sliding forward with respect to B. So B will apply a backward friction on this. So that will be a kinetic friction. Okay, which will be like this. So B will experience an equal and opposite kinetic friction in the forward direction. Now that kinetic friction on B, it tends to make B slide forward. So the ground will apply some sort of friction. Now we have to check whether B moves or not. So F1, now we don't know what kind of friction this is. This could be static or kinetic, depending. But I think it will be kinetic only, because the coefficient of friction was that way. No? So this coefficient of friction was 0.1 only. Okay, so we'll check. Okay. So under the action of this, what will happen in ground frame? A has an acceleration like this, rather it has a deceleration like this. Okay, and for B we have to check. Now for F2 is equal to mu2 into weight of A. So it is 0.5 into 4 into 10. So it's 20 newtons. Okay. Whereas F1's maximum possible value is mu1 into the normal reaction with the ground, which is 0.1 into 4 plus 1 into 10. So 5 newtons, correct? Is my calculation correct? Okay. Yeah. Okay, so that means we can see that the Planck also slides from t equal to 0 onwards. Okay. And because of that, now we know that this is kinetic friction, is not static friction. Okay. And we know that this has a forward acceleration AB, let's say, and this has a deceleration AB. Okay. So now from dynamics we can find out that in the ground frame, so all this I made with respect to ground only. Okay. So I can see the deceleration of A will be mu g for it. Okay. That's the standard case. So it will be mu2g. So it will be 5 meters per second square. Whereas the acceleration of B, that will be F2 minus F1 divided by mass of B. So 20 minus 5 divided by 1. So my God, it's 15 meters per second square. Okay. So it's a pretty strange kind of situation, but anyway, so this is what will happen. Okay. So we will see that velocity of A is V naught minus, okay, and velocity of B, okay. So slipping stops when velocity of A is equal to velocity of B. From that moment onwards, slipping stops. Or you can understand this with relative motion also. Also understand it this way, that this has a relative acceleration because they were accelerating the ground frame in the opposite direction. So it will come to rest at some time t. So that will be like this. Okay, so my V naught was 8 meters per second, and this relative acceleration is becoming 20 meters per second square. So 0.2 seconds. Oh, sorry. This will be how much? 0.4 seconds. Okay. So now we have to check the relative displacement in 0.4 seconds. So if this relative displacement is more than the length of the plank, then it will. Okay, so the displacement of A with respect to the plank will be V naught square upon 2 times the relative acceleration. Point 0.4 meters. Is that correct? Something wrong now. It will be 1.6 meters. Acceleration of A, Nishit. Yes, it seems very unnatural, but it will be like this because the net frictional force on A, you can see from the free body diagram. Acceleration of which one, A or B? Acceleration of A. A is very simple, बेटा. A पे एक ही friction act कर रहा है ना. This kinetic friction. Okay, good. Okay, B you got, na, Nishit? Sorry, I was saying something is wrong here. Yeah, this is 64 by 40. So this will be 0.16 or 1.6. 1.6 meters. Okay. So now this 1.6 meters is less than what we've taken as the length. How much was the length of the plank? 2 meters. Yeah. So this is less than the length of the plank. So A does not slip off. So now, first of all, with respect to the plank B, okay, the maximum displacement of A is going to be this only, 1.6 meters. But in the ground frame, it's something more interesting, because in the ground frame, what is happening is that at t equal to 0, they start off like this. Then, let's say, At that time t equal to what was it, 0.4 seconds. Okay, they have a common velocity now. Okay, and they have a common deceleration. So eventually, at some time, their common velocity is going to be 0. So this will be the maximum displacement of A in the ground frame. Okay. So you can see that from t equal to 0 to t equal to 0.4 seconds, A slips on B. So therefore, acceleration of A with respect to ground is minus of uh, 5 meters per second square. Okay, and the initial velocity of A with respect to ground was 8 meters per second. So during this time, the displacement of A will be 6.4 meters. Okay, but then from t equal to 0.4 seconds onwards, okay, acceleration of A is equal to acceleration of B, which is negative of the kinetic friction on the floor divided by m1 plus m2. Because as a combined object, they have that thing acting on it. So kinetic friction on the floor was, if I remember correctly, yeah, it was 5 newtons. Okay. So they have a combined deceleration of minus 1 meters per second square. Okay. So the further displacement that A makes, let's say SA prime, will be this velocity upon 2 into 1. Now what is this velocity? V is the common velocity at t equal to 0.4 seconds. Okay. Okay. So the net displacement of A with respect to ground is this much. This net displacement. But from 0.4 seconds till whatever this time is, which also we can figure out, okay, because the common deceleration is 1 meter per second square, so 6 and 1, so this will be, this time will be 6 plus 0.4 or 6.4 seconds. So during this time from 0.4 to 6.4 seconds, there is no relative displacement. So the relative displacement is only happening in the first 0.4 seconds, but in the ground frame, they're moving as a common object. Okay, okay. So hope all the values are clear, people, in this question. Okay, so we will conclude today's session here. Now, like I told you, I'll be giving you a question to solve with the application of relative motion. So in this question, what is happening is at t equal to 0, so A and B start at time t equal to 0, as shown above, such that B moves with uniform velocity BB, and A moves with a uniform speed VA, such that its velocity always points at B. Okay, so basically, initially B is going off like this, and A is chasing it with a velocity VA like this. But after some time, let's say B has reached somewhere here. So B continues with this velocity like this, but by then A would have reached, let's say, somewhere here, and A's velocity is directed towards B. So B will have a straight line 1D motion with uniform velocity, whereas A will keep curving in its direction. So it will keep curving like this, and eventually they will meet somewhere. So you have to find the time in terms of VA, VB, alpha, and D when A hits B. Okay, so this is the example problem of application of approach velocity concept, which I want you to try. Okay. That is instantaneous relative velocity of approach concept. What I want you to try. Okay. And next lecture, we will be looking at multiple pulley systems, then wedge systems, non-inertial frame and pseudo force. Okay, and also dynamics of circular motion. Okay. With focus on constraint relations, okay, friction, limiting conditions, and so on. Okay, so we will complete this portion, then we will come to the work energy and application of work energy in vertical circular motion part next, and then eventually to momentum conservation, system of particles, and rotational mechanics. Okay, so that's it for today's session. Those of you who sent me doubts on WhatsApp, I will reply back as soon as possible with some hints and questions. Okay, and if required, we will discuss them in class, or I will set aside some time for that. Okay, so that's it for today's session, people. Thanks a lot for attending, and wish you all the best. All of you done very well in the mains, and it's an indication that with proper focus preparation, you can secure a good rank in JEE Advanced. So I think you should go all out for JEE Advanced now, and that will also give you the benefit of improving your marks in your next JEE Mains if you so desire. But focus completely on JEE Advanced now. That will be to your maximum benefit.